Welcome back, everyone. Thanks for sticking around for the session too. So for me, who have just joined, so this is Pavan. I'm a senior platform engineer at Grainger. Uh, Now we are going to talk about what runs on the HPC cloud workloads and machine learning and scientific software stuff. And in the session 1, we dealt with the various GitOps platform like Argo CD, Crossplane, and Kada for the fleet management. But now building a shiny Kubernetes cluster doesn't matter if the data scientists or researchers can't run their MPI jobs or other utilize GPUs effectively. So in this talk, we are going to we're going to shift our focus mainly on infrastructure to concurrency scientific workloads. We'll break down into 5 pillars. So the first one concentrate on HPC containers, the second one for the advanced orchestration, and the next one is for the FinOps and for the deep observability, and finally P2P architecture infrastructure. So. So there's a persistent myth in the scientific community that containers add too much overhead for the compute heavy workloads. But our goal is to prove that we can achieve less than 1% of performance overhead compared to the bare metal one. So how do we do that? First, we bypass the virtual networking overhead by using the host networking to give MPI traffic direct to NIC access. And second, we leverage with SRIOV for the hardware level virtualization, and which gives us near bare metal InfiniBand performance. Finally, we use CPU pinning to guarantee the dedicated codes, eliminating context switching, and ensure NUMA-aware memory allocation. So let's come to the pillar 1. So that's where we heavily work, so we start. So this is a sample Docker file where we start with a base image like NVIDIA CUDA base image, and we pin exact versions what we are going to download from that, and we start we installing heavy dependencies like the libnet CDF or GoFortran right alongside with our modern Python scientific stack like NumPy or X-Ray. We compile our Fortran modules during the build stage. This guarantees us the stimulation environment is 100% immutable and reproducible. And so once we have the image perfectly fine, so now we need to deploy them onto the cluster. So that's where we deal with the so generally for the Kubernetes scheduler, how it does in the sense, it is good for the microservices, but it is never designed for tightly coupled MPA workloads. So the default scheduler, pod by pod decisions. So whenever a pod request comes, the schedule thinks, OK, it has to be allocated on so-and-so workload, so it deploys into that. But this leads, so what happens whenever a 3 CPU resource pod comes and tries to deploy in it, and you have 4 GPUs that are available, and job grabs the first one, and the next one, it's waiting for it. It will wait for long till another node is up and running. So that's where the MPA needs all has to be atomic scheduling. So that's where all the pods has to be scheduled together and the exact time with a dedicated CPU allocation. So that's where the solution is gang scheduling. That's where we can implement tools like Volcano or Q. So where we have, for example, if you see the job manifest, whatever we have it. So here the replicas says 8. So that guarantees exact 8 replicas, and all will start simultaneously. So that makes all or nothing. If you have a job that's coming up, so it makes sure all the 8 jobs are running at the same time, so that there's no GPUs wasted, or someone has to a specific pod has to wait for to be scheduled. So the result is no parallel scheduling, no deadlocks, or no absolutely wasted GPUs or sitting idle while it's waiting for siblings to spin. So then next comes the pillar 3, where is the predictive FinOps. So running all these GPUs are pretty expensive, especially with the bursty scientific workloads. Reactive scaling, too late. You wait for the pod to get into pending state, and then you suffer a 5 or 10-minute delay while waiting the heavy GPU node starts up. So that's where you can do a pre-warm nodes. So this causes massive queuing during the peak times. To solve this, we move to a proactive time-based scaling, and we pre-warm the nodes before peak hours and mix a spot and on-demand instances aggressively scale to 0 during the quiet periods. So I can show you an example of how the Karpenter node pool looks like. So you can have like as many node pools as you want, and you can define. And if you see clearly, so the key point over here is like the node instance type. So that's where you define whatever the instance available. So how it picks in the sense like whenever you define a job with a CPU limits, and that's where it looks for the CPU request and it allocates, okay, Karpenter decides, intellectually decides where exactly this has to be landed on which node pool. So that's where it creates a node for that and then schedules the job on that. And that's where the CPU limit, resource limits are so crucial, like whenever you define the limits and then the resource requests, so you have to define like a precise values, and that creates a best instance for you at the time of scheduling. And there's one more key value is like you don't need to define a specific instance. You can define a family of instances, so that picks up whatever it's required best for your workload. And there's one more thing I want to highlight over here is like the consolidation policy. That's where like combined with the like consolidation policy with underutilized policy. So the Karpenter reclaims the underutilized one nodes whenever the configuration is not like enough, that's not allocated onto that. So it will automatically scale down the nodes, and if there's no enough workload that's running up. So this significantly reductions in the like our compute costs. So this is one of the feature one that we want to use it heavily. And there's one more thing I want to spot is like the values, the capacity type. That's where we define spot and on demand. Of course, generally it all depends on the company, like whatever we have with that vendor. But the thing is like the spot instances are a bit cheaper, and whenever you have a random job that you want to run on the fly and just go away with it, that's where like it picks up the spot instance for you. And sometimes like if you have a like a tie-up with a specific vendor, so that's where you go with a on demand, so that's very cheaper compared to spot. Sometimes it depends on like what are the terms we have it with it. And the another pillar I want to is like deep observability, as I mentioned before. So here we define an hotel scrape metric, so where we define a specific to scrape metrics using NVIDIA DCM exporter. So this gives us a granular hardware level data straight into Prometheus, and we scrape the metrics and store them, and we see, okay, what is the it's taking up and where exactly we are lagging behind, so that like we can see, per GPU utilization or memory bandwidth or temperature throttling or even the specific pipe activity. And implementing the hardware visibility. So this is where the massive discovery happened for us. So we noticed like frequently using 8 GPUs of the machine, but the jobs in just in case like they are not using exactly the same ones, because they might be expecting a huge bump, but the thing is like in reality they don't have like enough GPUs that are using, so it can scale down whenever we need it. So that's where like it really helps like the like OTel really helps there. And the final one is the Dragonfly. That's where like we spend like generally millions of dollars provisioning the massive high performance GPU clusters for our scientific workloads. But getting the compute is the halfway. The reality we are facing is like the network because new bottleneck. So if you look at the left side of the architecture, that's where like the standard K8 one, like Kubernetes one, so where the OSA registers pull the images or like all the catching stuff happens. But if you say the upset, like if you're doing it for the LLMs or like the massive tensor weights, so this doesn't exactly work. So that's where like, for example, let me take an example. Like if you have a 200 node GPU cluster and a new model type drops, and the standard Kubernetes schedules will trigger these pods simultaneously, and there is like almost like 26 terabytes of network traffic slamming your original server, like whether it may be the Hugging Face or model scope or any other internal registry at the same time. So what it happens? It happens like your IP rate limited, or your NAT gateways get saturated, or you even pay the exorbitant egress fee for that. But worst of all, your GPUs are still waiting to be scheduled, and your pods are still waiting in a create state. So this is where like there's an tool like Dragonfly. So this is where the architecture fundamentally we need to change. So we need to stop treating this the MI workloads, like ML workloads, as like traditional static container images. So that's where like the peer-to-peer infrastructure able to resolve that. To solve this, we recently worked on like one of the CNC Dragonfly project. That's where like the peer-to-peer distribution protocol happens. So instead of 200 nodes pulling all from internet, the cluster pulls the exactly once in a seed peer, and this seed peer from there, the nodes form a local mesh network. So that's where the microtask or transform model chunks literally across your local network with a high-speed switch fabric. By natively integrating this Hugging Face or model scope protocols into your daemon layer, we shift like massive data payload from the egress gateways and no need onto the local mesh. So the result is like instantaneous like pod startups or even the 1,000-node clusters and through agentic ops. So this means we can finally scale like all the agentic swap models on the fly without holding like huge GPUs, hostage, or anything else. So yeah, when we put all together like infrastructure as a code or the GitOps, whatever the practices I talked before. So these 5 pillars, the optimized containers or gang scheduling or even the FinOps cost savings, which tracks with a deep observability and accelerating P2V, the results speaks themselves. Like we maintain like almost like 1% overhead, and we achieve like better results for that. And we saw like almost 34% cost reductions in Karpenter, and plus like 50K monthly savings around with the only hardware waste what we are doing with the open telemetry logging stuff. So yeah, any questions? Yeah. Sure.
Sorry if I missed this. Did you say using a custom Kubernetes scheduler?
Sorry?
Did you say you're using a custom Kubernetes scheduler?
Yeah.
What was that again?
It's a gang schedule. It's Volcano.
Oh, okay.
Yeah, Volcano or Q. So you can use either of it. Both of them are the project, open source projects. Yeah, thank you. Any questions? Okay.